Okay, so in this video I'm going over acetal formation and then also the backwards of that reaction, because when forming acetals the reaction can go in equilibrium. So we're going to do it both ways. We start with an aldehyde and an alcohol, and this reaction has to be catalyzed by something. I've always seen it with a strong acid, but we just put a proton there to let us know that it will be catalyzed. So the reason why we have to catalyze it is because we know that oxygens are very electronegative. So this bond, this carbon-oxygen bond, has a partial negative on the oxygen and a partial positive on the carbon. But when our oxygen grabs onto the hydrogen inherently being catalyzed, this is what we get. And we know that oxygen is already partially negative, but now it's positive. So in order for this carbon to counteract that positive charge, now it's super positively partial charged. So now this is a really good electrophile. So our nucleophile comes in, which is our alcohol. The oxygen will attack the carbonyl carbon, which will make this double bond break and give a lone pair back to the oxygen. So now we have a tetrahedral structure because we have 4 substituents. This is the oxygen that was a part of the carbonyl, and now we have an alcohol attached. But this oxygen is positively charged because it has 3 bonds and 1 lone pair. So its valence electron number is 6 minus its 1, 2, 3 bonds, and then its lone pair. So that's 5 equals a +1 charge. That's why it's positively charged. So in order to get rid of this positive charge, water in our big solution and our big bucket of aldehydes and alcohols, our solvent is generally water or some kind of acid. So the oxygen will grab onto the hydrogen, and then we have a happy molecule. And this is called the hemiacetal. Oh, I forgot my hydrogen right here. Sorry. Okay, so now we have our hemiacetal. This is the first thing that we're making in our reaction. I like to separate my reaction into 3 big chunks, and the first chunk is that we make the hemiacetal, and I'll explain the rest as we go. So here we're starting with our hemiacetal, and now we have to form our acetal. So right now we have an OH group and an OCH3 group, and in order to form the acetal we have to get rid of this OH group. So a good way to do that is to literally make it leave, and the way we can do that is have the oxygen on the OH group grab onto a hydrogen from water, so that it has 2 hydrogens now, and that makes it have a positive charge. And this H2O plus looks a lot like water. So what happens is this comes off as a leaving group. And when that happens, a lone pair from the OCH3 oxygen will fold over and form a double bond, because if this water left with nothing to replace the bond that was there, then we would only have 3 bonds on this carbon, and that's bad. So this oxygen bond or lone pair folds over, and we have an OCH3. This is positively charged. I keep forgetting my hydrogen, I'm sorry. And now what we have is the hot electrophile. I'm not sure if this is a scientific term for it, but this is the way I always learned it. So similar to how this molecule was a really good electrophile because this oxygen was positively charged, this is the same kind of thing. So a lot of the molecules in this reaction look very similar, which is, I think, make it a little bit easier, but here we are, keep going. This is what we have, our hot electrophile. And now, in order to get rid of that positive charge, we have a oxygen come in, attack the carbonyl carbon. This is a second alcohol molecule in our big bucket of solution doing the same thing that we saw before. That's the OCH3 that we had before, and this is the alcohol that just attached. So, just like last time, we take off the hydrogen from here, and now we have our final product, OCH3. Okay, and this is our acetal. So this reaction had 3 big chunks. I'm going to highlight everything as we go through. So I like to use colors to use on these reactions because there's a lot of stuff going on, lots of arrows, movement, and I think that using colors helps put everything together. So this oxygen grabbed onto a hydrogen and became a wonderful electrophile. Then our alcohol is swooped in, and now our OH is happy because it has 2 lone pairs and 2 bonds. This oxygen stays the same once it's in the hemiacetal form. And then from our hemiacetal, this oxygen grabs onto a hydrogen in order to become a really good leaving group, and it comes off as water. And this is the last time we ever see that carbonyl carbon, the original one. So I'm going to use a different color, follow a different oxygen. We're going to follow the first alcohol nucleophilic oxygen. It comes in, attacks the carbonyl carbon once we have our pretty electrophile, and then we have to take off its hydrogen in order for it to be happy and have 2 lone pairs and 2 bonds from one charge of 0. In our hemiacetal form, it kind of chills out in this step, lets oxygen leave in the form of water, folds over, and then forms our new double bond. This is our hot electrophile. In our hot electrophile form, right here, we have our second alcohol join in. Now, oops. Oh yeah, that's the right one. So, after the new alcohol came in, now it has 2 lone pairs and 2 bonds. It's happy, and here it is again. And then our last alcohol came in at this step, grabbed onto the carbonyl carbon. We took its hydrogen away in order to make it happy, and here it is in the final step. So, hope that made sense. I realized that I kind of blew through the last couple steps, but I feel like once you see this first chunk, when you form the hemiacetal, everything else looks pretty similar because this molecule is very close to this molecule. And then you really do the same steps. You have a nucleophile come in onto the hot electrophile, whatever it may be, and then you take off its hydrogen, and then the next product that you have is more stable than what you had before. That's what happens here. This second alcohol comes in, attaches to the carbonyl carbon, we take off its hydrogen, and then we have a happy new product. So, I'm going to do a different video for the reverse reaction, but hope that made sense. Let me know if you have any questions.